With deductive arguments, we spent a lot of time rigorously symbolizing their form. It's not quite as easy to give the form of an inductive argument to evaluate its strength, but by looking at a few types of inductive arguments, we can begin to characterize what makes a stronger or weaker argument of each type. So in this lesson, we're going to look at 5 broad types of inductive arguments: enumerative induction, statistical generalization, statistical application, argument from analogy, and inference to the best explanation. And we'll get a general sense of what makes arguments of each of these types weaker or stronger. Enumerative induction is the most basic type of inductive argument. In this form, we reason from the fact that there's been a past instance or a previously observed instance with certain features to the claim that the next instance will be the same way. So something will have the same features, something will have the same characteristics, an event will be similar. For example, we can reason from the past instances of the sun always rising in the morning to the fact that we'll observe the sun rising in the morning tomorrow too. Or we might reason from being bitten by an unfamiliar dog in a past instance to the likelihood that we'll be bitten by an unfamiliar dog in a new instance. In general, stronger enumerative induction will rely on more past observations, like in our first instance. By contrast, an argument that appeals to a single past instance, like the second argument, makes the conclusion only slightly probable, given that evidence. And while it's common to make those kinds of hasty generalizations in this second argument, the problem with them is that they fail to consider what circumstances may or may not make the dog biting incident likely to be repeated. Sometimes we find a quantifiable pattern in our observed instances. We might notice that a certain percentage of them have some feature. That's the starting place for 2 kinds of statistical inferences: statistical generalization and statistical application. In statistical generalization, we reason from what is true about a sample of a population to what's true about the population as a whole. Polling would be the key example. With statistical application, we reason from what is true about a population as a whole to what might be true about a subset of the population or an individual in that population. So here's a polling example of statistical generalization. In a poll of over 20,000 Americans, over half supported a transition to only using clean energy in the next 15 years. From that, we infer that over half of all Americans support a transition to only using clean energy in the next 15 years. So in this actual polling example, a sample of 20,000 Americans were asked their opinions on clean energy, and from that, the pollsters made an inference about all voting age Americans. This is a pretty strong inference. The criteria for a strong statistical generalization just demand that it draws on a representative sample, because the sampling is unbiased. So we want a representative sample of Americans that captures the variation among them. And the sample should be large enough that it is likely to be representative of the whole population. So 20,000 Americans in this poll is a pretty large sample, and most polling firms do some extra calculations to make up for any possible bias that might come from any unrepresentativeness in their sample. Statistical applications reason from what we know about distributions in a population as a whole to what's true about some subset or individual in that population. This means that often statistical applications depend on previous statistical generalizations. So the generalization goes from sample to the whole population, and statistical application goes from whole population to an individual or subset. For example, this is a statistical application about people who purchase lottery tickets. So only 0.0000001% of people who purchase a lottery ticket win. Let's say that's true. And that Faye bought a lottery ticket. We can infer then that Faye's ticket was not the winning ticket. This is a strong statistical application. That's because a good statistical application involves reasoning based on what's true about close to 0 or close to 100% of a relevant population. That makes it more likely that the claim is true of a particular individual. So in this example, we have almost no lottery tickets winning the lottery, so it's likely that Faye's lottery ticket isn't a winning one either. Beyond generalizing from past or previous instances, or what we know about a group, to instances we haven't observed yet, one of the main reasons we use inductive inferences is to infer the causes of effects we observe in the world, and also to predict the effects of certain kinds of causes. So normally we call prior events or changes that immediately precede some phenomenon the cause of that phenomena. In particular, it's the event or change, something that happens. That's the cause of some effect. We want to not only identify individual causes of particular events, we're also interested in making causal generalizations about which kinds of causes lead to which kinds of effects. These are particularly valuable when we want to predict the outcomes of future events or actions. For example, we're familiar with the generalization that gravitation causes things on Earth to fall when we drop them. So even if you're not familiar with the gravitation laws, you can use this predictive power. You know how things behave so that if you drop a pen from the top of your desk, you can predict that it will fall to the ground. But there's a question: how do we get to these causal generalizations, or a knowledge of what has caused a particular event? Well, perhaps the most common way we infer what caused a particular effect is through a type of inductive inference known as inference to the best explanation. This sometimes gets called abductive inference, but it's really a kind of inductive inference. And when we look to infer an explanation, what we want is an answer to why or how questions, and to generally characterize some cause-effect relations. So we want to know why or how some cause led to its effect. And that means that in inference to the best explanation, we have an observation or set of observations of effects and infer the cause that best explains that evidence. So the explanation is not something we directly observe. Instead, we have some observations and we infer the truth of the explanation from what we observe. Now, there are no formal rules for what makes the best explanation, but we can give some guidelines for what makes a better explanation. And the best explanation should be the likeliest one and the loveliest one. So let's consider what those two terms mean. The likeliest explanation is the one that's most likely to be true. So what makes something a likely explanation? It would be one that explains all the observations, but it doesn't make additional assumptions that might be implausible or unwarranted, and it doesn't contradict well-established truths. The loveliest explanation is the one that best helps us understand why the cause led to the effect. In general, so-called lovely explanations are ones that are simple, that don't themselves require further explanation for us to understand them, and which also could explain similar cause-effect relations. A likely explanation wouldn't involve assuming that there are witches or denying the existence of gravitational forces. And a lovely explanation wouldn't involve an unjustifiably complex system. So let's look at an example both to characterize how inference to the best explanation works and what makes for a good and bad explanation. So here's the observation. It's morning, you enter the kitchen, you find a plate and a cup on the table, there are breadcrumbs and a pat of butter on the plate, and it's surrounded by a jar of jam, there's a pack of sugar, an empty carton of milk. You infer that what explains these observations is that one of your housemates got up in the middle of the night, made themselves a midnight snack, and they were too tired to clear the table. So you reason that that's the explanation of the observations you find in front of you, given that you know you have housemates, maybe you know that they have this tendency to eat snacks, and they're the only ones who would be likely to be there to eat snacks while you were asleep. Now we can think of some alternative explanations. So it might be that someone burgled the house and took time to have a bite while on the job. It could be that your housemate decided to arrange all the stuff on the table so it looked like they were having a midnight snack, even though they didn't. These alternative explanations, though, fail our tests. So the burglar explanation requires making unwarranted assumptions about why nothing is obviously missing. So that's not a very likely explanation. And the faked snack example depends on looking for further explanations for why your housemate would pull such an odd prank. So that's not a very lovely explanation. Attributing all the mess to your housemate explains the observation without making unwarranted assumptions or requiring a more complex explanation. The last type of inductive argument we'll look at is argument from analogy. These types of arguments are particularly valuable for generating hypotheses that can be tested with further examination. And arguments from analogy are structured as followed. You take two things, objects, phenomena, events, that are similar in several respects. And then you infer that they're similar in some further respect. So we can give this a kind of premise-conclusion form as follows. Entity A, again, that could be an object, some phenomenon, an event. It has properties P, Q, and R. And then we can take a few other things. B, C, D. They also have these features, P, Q, and R. These entities B, C, and D, our broader category, they have this other property, Y. We don't know that entity A has this property Y, we haven't observed it, but we can infer by analogy that if B, C, and D, which are similar to A in some relevant respects, have this property, A probably has that property Y too. We have terms for these two categories. There's the source domain, so those are the set of objects and claims about their properties that are the basis for the analogy. So in this example, that's B, C, and D. And then the target domain is the object or objects we're making an inference about. So we're trying to infer that they have a certain property. So in this case, that would be entity A. Why are arguments from analogy good sources of hypotheses? Well, the argument gives us a tentative conclusion about some property that A has, Y. And then we can go on to possibly directly test whether A does or doesn't have that feature. But we have a starting point for investigation. So let's look at an example. Premise 1, last year in California it was abnormally hot and there was a drought. This year's conditions are similarly hot and as dry or drier. Last year's fire season in California was bad. This year's fire season in California will be bad. That's our conclusion. So those premises are represented in the chart. The known properties are in the top 3 rows, and the top 2 rows represent the shared properties. Then we know that 2020 was a bad fire season, and so we infer by analogy that 2021 will have a bad fire season. So we could use this information, for example, to prepare for some fires, and then we could get some direct data later on about whether or not the fire season was as bad as we hypothesized it might be. Stronger analogical arguments are ones that have more features in common and more important features that are similar and more relevant similarities given the topic of the inference. These 5 types of arguments we've covered give us some general distinctions between types of inductive inference. Over the course of the next few weeks, we'll come back to these types of arguments, but in the next lesson, we're going to shift our attention somewhat to more formal tools and introduce some concepts that are fundamental to understanding and characterizing the rules that underlie probability calculations.